Dom? Mike? Oh God. Distance. Sorry.
We've got two of them, we can do a duet.
Oh. I'll hold it like that, like, you know. Hey,
Lemmy.
I'm part deaf. I've never been in a band. That's my opportunity.
Stealing my introduction. So, I hope everyone's had a good day. Has everyone had a good day? Has everyone had a good day? God, you're useless. It's Britain, isn't it? Has everyone had a good day? Shut up. So, to bring today to a glorious close, I would like to introduce, and I'm going to have to, I haven't got my glasses either, it's Danny. Papa Maximo?
Yeah.
Excellent. Again, showing my British roots. Funny foreign word, can't read it. So I'm going to predict the future using old school maths. There is going to be a fantastic talk, and we're all going to give a massive round of applause at the end. Let's see how correct I am. I give you Danny.
Thank you. Thank you, Dom, and everyone for having me here today. It's a pleasure to talk here again after a couple of years. So, first of all, let's have a drinking game later. Let's see, after a few drinks, can you pronounce my name? The one that loses just has a shot or something like that, or a sip of Coke. So, this talk is going to be short. It's going to, and the scope is to help us all understand what is inside the machine learning models, especially the talk of the month. It's the neural networks, deep learning, deep neural networks, artificial intelligence, all that. I only have one equation or two. If after this presentation, we all can describe to our friends at the pub what a neural network is, we have won. And also, there's going to be Pokemon. So this is something to talk about at the pub. So who am I anyway? I'm a senior lecturer at the university in Sheffield Hallam. I have a few things that I like. I like maths, Pokemon, coffee. I'm constantly caffeinated. I like knots, as in knot theory. And any jokes about knot theory is the most useless subject of maths. I'll take them, and I will ignore it because I like it, and that's all that matters. I dislike sardines, and I trust you. And that can go, so I'm a little bit naive sometimes. I trust the manual. I read the manual. I read the washing machine manual. I don't trust computers, and I work in tech. All of these likes and dislikes are part of my personal biases and opinions. Okay? I dislike sardines. You can like them. Sardines are not affected by my personal like or dislike. So I want to highlight that all these parts of personal traits for my own viewpoint. And reality, or data, facts, can prove me wrong. Okay? Maybe I should trust computers. Maybe I should believe that behind this user interface is something that does the job properly, and for a change, I don't need to take my notebook and back calculate everything and not sleep until I find out that this result is valid because I just walked backwards and I got the input. So one day, maybe we'll trust computers more. In machine learning models, there is a database, the very famous database called the IRIS dataset. And it's a very good dataset to train, to teach machine learning, to show people how classification works, how different machine learning models work, how KNN, K nearest neighbors, works. But I looked it up a little bit more, and I'm not going to use it today. I found out that this data set was published in the Annals of Eugenics in 1936 by a gentleman called Ron Fisher. And it was used in support of eugenics. This gentleman spent all his life believing in eugenics. So this did not age well. And I do believe that our data sets should stand the experiment of time, and maybe we're not going to use something that was used to promote a theory that, you know, if it was successful, some of us wouldn't be here today. So I'm very grateful that eugenics are massively debunked. And yeah, no one publishes, even in 1936, in eugenics, and something that is called eugenics something, by mistake. And this is something that I dislike, not because of my personal bias, but because facts. So I'm very happy that for once my dislike and my facts are meeting, unlike sardines. So let's see how my data set is going to age, right? Because I spent some time dishing this data set, the iris data set, this and that, but I decided to use the Pokemon data set. Let's see how this ages. Imagine like in 10 years, someone watches this video and says, Pokemon was promoting this, this and that, and we didn't know it at the time. So maybe in 10 years, you will see me under my video commenting like, I didn't know, I'm so sorry, please delete this video, I'm so embarrassed. And it's fine. I will, you know, I will grow old, but I will have fixed any mistakes I made. I like Mr. Eugenics. So what is a Pokemon? It's a cartoon that I grew up with. And it stands for Pocket Monster. It comes from Japan. Before any of you starts talking to me about anime at the pub or any other Japanese cartoons, I have no idea. I only know Pokemon. The reason why I know Pokemon is because there is maths behind it. Not knots, unless Ekans ties himself into a knot while in battle, but that's a different story. So they're cute, and there is a whole franchise behind Pokemon. They have games, they have the cartoon. I'll stick to the cartoon. I never played Pokemon games. So in the Pokemon universe, in the Pokemon cartoon, you have a few goals. Number one, to explore the world, the universe. Number two, to collect Pokemon from the Pokédex, which is very clever to call something Pokédex, right? Like Attendex, like attendance index. You can add text to everything. And it's pretty much like filling a sticker album, but with Pokemon. You are a Pokemon trainer. So you form teams of 6 Pokemon, and every team, you train it for battle. So you get your 6 Pokemon, your opponent gets 6 Pokemon, and they battle with each other. So which Pokemon will win? Before we find out which Pokemon is going to win, I'm going to tell you about a story about Pokemons going to the seaside. So you can see on the top left, Ash Ketchum. He's the protagonist of the series, and all his Pokemon. And he has a Fiat 500 for no other reason than because in Italian it sounds really amazing, and I grew up calling it Fiat 500, and then someone told me it's 500 here. So yeah, there we go. 500 sounds better. Sorry. So Ash has this little car, and not a Cybertruck, because he knows better. And also it can fit more Pokemon. The question is, how many Pokemon can Ash fit in his car? He wants to fit as many Pokemon as he can, right? Because they have feelings. And they all want to go to the seaside and have a good day. From the Pokemon data set, yes, there are a lot of Pokemon data sets. It's fascinating. We can see that there is a great variety in height. So you have a Pokemon that is called Joltik, and it's 0.1 meters high. And they can go as tall as 3.8 meters high. So now you end up with a situation like luggage Tetris, like how many Pokemons can you fit in the car? How are you going to position them? Which one should you choose? And from the Pokédex, how many Pokemon does Ash actually have? It's like how many clowns you can fit in a car, but unlike Pokemon, clowns have a smaller variance in height. one can expect. So it's getting a little bit more complicated. So now where is this all going? To the seaside to begin with, but also we need to find a common denominator, because at the moment the Pokemon have nothing in common. In the Pokemon universe, the Pokemon live in a Pokeball, which is a static state, where it's like the little house. And they're called out of the Pokeball during the battle. So you've seen probably on the telly, like Ash I'm throwing this Pokeball, or you've seen a Pokeball somewhere sold in stores. So this Pokeball has a specific size. You see where I'm going with it? Put them in a Pokeball and calculate how many Pokeballs you can fit in your car. So try to find the commonalities within your data set. Now you will ask me that, you will tell me, and you will be right too, that it wasn't in my data set. This information wasn't given to me when you gave me the tables with the height, the weight, and the attributes of each Pokemon. What was this all about? Before we do any analysis, we need to know your data. I spent about 10 minutes talking to you about Pokemon, not because I want to flex my knowledge of Pokemon. I'm 40 years old. Okay. Doesn't look like, very smart with some people's standards, a lecturer talking in a keynote about Pokemon. But what I wanted to tell you is that I have to know my data. I have to study my data and know the context before I try to do any analysis. Metadata and descriptors are really important for this. And I have to look for commonalities and patterns before I even start putting things in the machine, before I even start typing things in the computer. And this is where my distrust begins. How well do we know our data? So after we spoke about Pokemon for 10 minutes, we're going to use machine learning to see which Pokemon will win in the battle. This is the Pokédex, and we have some information about Pokemon. You have the name, the total points, the hit points, attack, defense, special attack, special defense, and speed. Given these attributes, how can I fit them in a neural network and find out which Pokemon will win? If you think that the use of Pokemon is quite naive, you can replace this with any other classification problem. You can form your own narrative. So let's look at Bonsley. Bonsley has an attack of 80 and a defense of 95. If I multiply his attack by 0.05 and his defense by 0.03, and I add them, and then add -3, deduct 3, which I will call the bias, I will get a number called 3.85. Why am I doing this? I want to calculate, using the attack and his defense, what is the probability of Bonsley winning? So I have this value of 3.85, and I put it in the sigmoid function. The classic definition of the sigmoid function is that it gives us the probability of existence of a class, so it's 0.89. So what happened just now? We had two inputs, attack and defense. We added some weights and a bias, and then we got something that we can call a probability under certain circumstances. If you understand this concept, congratulations, you just programmed your first neuron, one of the elements of the neural network. So, well done. The activation function is the switch that shows that this neuron should be moved forward. So this calculation should be walked through the network. And this is what happens. You see the Pokeballs in the location of neurons. This is the switched on neurons. And this is a neural network. And we have one layer, as I showed you here. we have one location where we have a calculation with a set of weights. You can have different weights and biases on each neuron, and then another one. And here, you can add, for example, after you calculate, you used here the attack and defense, you can multiply with weights of one other attributes like special attack or special defense, and then add different weights here. So what is the difference between a neural network and a deep neural network? The number of layers. If it's more than 3 layers, including input and output, so if I had this, can be a neural network, I have an input and I have an output. If I add another layer, it's a deep neural network. That's it. And when I say that to people, they get really disappointed, like, yeah, it's a neural network with more than 3 layers. Oh, but it gets so much hyped, so I thought that I should tell you about it. In general, your input matters. What you put in the neural network defines its performance. I spoke about the heights of Pokemon before. We have Pokemon that are 0.1 meters high and 3.8 meters high. If, as an input, instead of attack and defense, I had height and weight, you will see here that the weight can be up to 24 kilos. So what's going on now? We have a magnitude difference. If I have a magnitude difference, chances are that different weights will be arbitrarily applied, and I will talk about this more later, by your machine learning model. So there is a way to deal with this, is that it's to normalize your data. But who defines the weights? Randomly at first. Doesn't sound very promising, right? And for people like me who say, I don't trust the computer, I need to back calculate everything. And I tend to annoy people by being like, I really need to verify the results. It is a little bit of an issue, but don't worry, because like Ash Ketchum, we're gonna train our neural network for battle. So we optimize it for training. You trust the process, but do you trust the machine? Do you trust that the weights applied to a data that has variables of different magnitude, like one is 20 kilos and the other one is like 3 meters, so you can have like 10 times bigger numbers. Do you think that the weights will be applied equally? I can tell you from all the back calculations and sleepless nights and lack of hobbies that even if you don't normalize your data, your neural network will work. In the end, it will work. But you don't have time, you might not have the processing power, you might not have the patience, and it's fine. So we normalize or standardize or scale our features. What does this mean? We try, one of the easiest things to do, and I will stick to that for now, is to make sure that all our inputs are between 0 and 1. The easiest way to do it is divide by the maximum value. So you find the maximum value on your column, divide all the values with this one, so you start from 0 to 1. Easy. So you have the same range. So your weights will be at the same range. I asked, how good is my network? Do I trust it? I decided to have only a few equations in this presentation because it's late, and there are better things to talk at the pub than what on earth was she about with all these numbers. So this is the mean square error equation, which in neural networks is also called a loss function. So it's 1 over n, and it's the number of observations of data points. And the summation of the predicted value of the real value, that's the reality, and that's the predicted value. It has error in its name, so even if you're not, if you don't like maths and you have every right to, as I told you, this is a personal like and dislike, if you see something that says error, you'll be like, yeah, I don't want much of it, do I? Instinctively. That's true. We want our mean square error to be as low as possible. So let's think of Barnsley. We've tried to see if Barnsley is going to win at the battle. And what is the mean square error? We have one observation, Barnsley. The reality is 5. The probability, the number in the bias function is, in the sigmoid function is fine. X is 5. And the other X is 3.85. And this is not right, because I should have put the Y, and the Y I calculated is here. So it should have been 1.99 minus 0.89. So there we go. Spotted an error. The loss function can also be explained as a function that includes the weights as variables and the bias. I forgot to tell you what the bias does. It shifts the function left to right. So if I didn't deduct 3 from here, I will be at 6.85, which is outside of my sigmoid function. So the bias just puts me in the range. You can avoid increased bias by standardizing your data or by scaling your data. So, any memories? No? Just, blank looks like, oh God, partial derivatives. So, if I say that this function with W1, with weight 1, weight 2, and bias is equal to this function, I will be right, because both of them are defining what the loss function is. So, what I want to find out is how much the loss function changes if my weight changes. So I told you that I've calculated arbitrarily these weights. I said 0.05. Why? Because I say so. Don't believe me. If I change this weight, this change will affect the loss function, the mean square error. And I want to see, am I making my model better or worse? I always want to make it better. So instead of typing in numbers, I want to be smart. And I want to see how far off am I. I know what happens in reality. I know what I have predicted. All I have to do is modify this weight, and then this weight, and then my bias. That's why we have computers. So I want to see if this increase is positive or negative. And insert the chain rule. It's the partial derivative of L, of the loss function, over the predicted Y over the initial weight. What does this mean? Why am I doing this? The good news is that unless you have a lot of time and you're really curious, you won't need to do it by hand. The bad news is that somewhere, someone has put the wrong numbers, has used the wrong activation function. There is the sigmoid function, there is the binary function. There are a lot of ways to make a neural network. Someone somewhere made a neural network that gives you the wrong predictions, and it's very easy. And you need to know, at least as a concept, where to look. That's my goal here. I don't want to know all the nitty-gritty details necessarily, but if I get a table of the mean square function outputs per iteration, I can see what's going on. So if the partial derivative increases, is positive, then the weight will decrease and the loss function will decrease. So we're always looking for a positive value. But if it's negative, then it will increase the W1 and the loss function will increase. The partial derivative here will increase. So our goal is to minimize the loss function. But if we minimize it too much, are we overfitting? So what did just happen? I used a backpropagation technique for our feed-forward network. Smart words. So, no, that's really what I did. That's how it's called in real life, or in, you know. So that's a backpropagation technique. I take my output, and I'm using it to adjust my neural network. I will do it again and again and again until I have a proper loss function that satisfies my condition. I might be overfitting though, so I need to be careful. I have to use the same technique for all our weights and for all our biases. So if you have a very deep neural network with more than 3 layers, as we said before, then you will have to do it again and again and again, not by hand. You have a machine, you can write code in Python, Rust, COBOL, yeah, Fortran, or, hey, I'm old, I like Fortran. What happened to Fortran? We'll talk about this at the pub. And our new weight, W1, will be W1 minus n times the partial derivative. Wait a minute, what is n? N is the learning rate. N is denotes how fast our network is learning. Excuse me, sir, you're sitting in front of the clock. And thank you. Sorry, I don't want you to spend more time here. I know that you have to go to the pub. I know my priorities, okay? So that's why I've been dancing a little bit. I'll call it the neural network dance. Okay, I'm cool. If I say it many times, it will be true. So that's it pretty much. That's old school maths. I limited myself to A-level maths, at least that's what one of my students told me. If he was lying, please let me know. And I've tried to explain all the concepts that I'm using to program a very, it's not simple, but a neural network that will work. All it takes is patience and a Casio calculator that has quite a lot of battery in it. So. But you can do it by hand, absolutely. So, congratulations. Now you can write your own neural network, and I hope that you have a lot of things to talk about at the pub today and that you had a great time. Thank you so much.